Teton Dam was 305 feet of engineered earth, brand new, built by the Bureau of Reclamation, and it failed the first time water pressed against it. On the morning of June 5, 1976, the engineers who designed it stood watching muddy water bleed from its downstream face, a warning they recognized but could not stop. What the reservoir found inside that dam had already killed before. The Bureau of Reclamation planned the Teton Basin project as a major federal investment to secure the agricultural future of eastern Idaho. Nestled in a steep volcanic canyon 15 miles southeast of Rexburg, the Teton Dam was designed to tame the river, storing over 288,000 acre-feet of water for irrigation, flood control, and power generation. Construction began in 1972, and by November 1975, crews topped out the massive zoned earthfill embankment. Standing 305 feet high and stretching over half a mile across the canyon, the structure contained nearly 10 million cubic yards of compacted soil and rock. To the public and agricultural districts, this colossal barrier represented the absolute peak of modern engineering confidence. Yet, the decision to construct the dam in this canyon bound its fate to the volatile ground beneath it. The steep walls consisted of highly fractured, rhyolitic ash flow tuff, a volcanic rock riddled with open joints and wide voids. This buried geologic reality meant the reservoir's containment relied as much on the fractured, unpredictable rock behind the abutments as it did on the engineered embankment itself. To block water from escaping through the canyon's highly fractured rhyolite, designers relied on a 3-row grout curtain. Crews drilled over 2,500 holes, pumping more than 9 million pounds of cement grout into the rock fissures under intense pressure. But a grout curtain alone could not guarantee an absolute seal. To block seepage along the upper canyon walls, engineers excavated steep-sided key trenches directly into the abutments. These trenches cut 70 feet deep into the volcanic rock, designed to be filled with impermeable material that would act as a subsurface barrier. The choice for that backfill introduced a major vulnerability. The Bureau used local loess, a wind-blown silt with very low plasticity. While highly compactable, dry loess behaves like loose sand when saturated, dissolving rapidly in flowing water. In standard dam design, a transition zone of graded sand and gravel, a filter layer, would wrap around this irredeemable core to catch escaping silt particles. Yet, at Teton, the design omitted this filter zone inside the key trenches. The highly irredeemable loess sat in direct, unprotected contact with the heavily fractured volcanic rock. Geologists and external reviewers flagged these risks during the planning phase, warning that the reservoir walls would transmit vast amounts of water. Rather than abandoning the site or redesigning the core with a protective downstream filter, the Bureau answered these concerns with minor design adjustments. They increased the grout volume and adjusted compaction specifications, leaving the core's fundamental vulnerability buried beneath millions of tons of earth. In the spring of 1976, rapid snowmelt from the surrounding mountains filled the reservoir at a rate of up to 4 feet per day, 4 times faster than the design's planned limit. By early June, the water level stood just 3 feet below the spillway. The immense hydrostatic pressure was now pushing directly against the unprotected loess core. Minor seeps had already appeared on the canyon wall below the dam in the preceding days, but on the morning of June 5, 1976, the character of the leaks changed. At 7 a.m, workers spotted a small seep on the upstream side. By 9:20 a.m, a wet spot appeared on the downstream face near the right abutment, venting water. Unlike the clear seepage expected from normal foundation drainage, this water was muddy. In dam engineering, muddy water is a critical warning sign. It means the flow is actively carrying soil particles out of the structure. The reservoir water was driving through the unsealed rock fractures, directly eroding the highly unstable loess inside the key trench. Internal erosion, or piping, was actively carving a tunnel through the dam. At 10:40 a.m, operators drove 2 bulldozers onto the steep downstream face, pushing rock and soil into the expanding void. But the internal pipe was already too large. The ground liquefied beneath the heavy machinery. The operators scrambled to safety, abandoning the tractors just before the widening chasm swallowed both machines. The dam was washing away from the inside out. At 11:57 a.m, the main embankment failed completely. In less than 5 hours, the muddy leak had expanded into a total structural breach, releasing approximately 250,000 acre-feet of water into the upper Snake River Valley. The resulting torrent swept out of the canyon with immense force, entirely erasing the small community of Wilford before inundating Sugar City, Rexburg, and Roberts downstream. The water carried away homes, vehicles, and irreplaceable topsoil, ruining hundreds of thousands of acres of fertile farmland. The human and material toll was severe. The flood claimed 11 lives and destroyed roughly 13,000 head of cattle. This was no longer just a localized design failure in a remote canyon. It was a regional catastrophe that permanently reshaped eastern Idaho. The independent review panel's post-failure investigation dissected the physical forces behind the collapse, framing the disaster as a clear case of piping. This internal erosion begins when water under pressure forces its way through a microscopic path. As water flows, it sweeps away fine soil particles. This loss of material enlarges the channel, increasing both the water's velocity and its capacity to carry larger particles, rapidly carving a hollow pipe through the structure. At Teton, this process became uncontrollable due to a critical material pairing. The highly erodible loess inside the key trenches was in direct contact with the heavily fractured volcanic rhyolite of the canyon walls. Because the design omitted a graded sand and gravel filter, the flowing water easily washed the silt directly into the open rock fissures. The panel concluded that the design lacked any backup systems, relying entirely on individual barriers that failed in sequence. The decision never to rebuild on the site served as the final verdict on these design choices. The collapse was the cumulative result of water steadily exploiting an unprotected, highly vulnerable foundation. The vulnerability at Teton was not a novel engineering puzzle, it was part of a recurring historical pattern. In 1928, California's St. Francis Dam collapsed, ending the professional career of Chief Engineer William Mulholland. While the concrete wall stood firm, the foundation of unstable schist and conglomerate softened upon saturation, sliding out from beneath the structure. In 1959, the Malpasset Dam in France failed under similar geological neglect. This was an abutment geology failure rather than a structural concrete failure, where high water pressure within the foliated gneiss tore the thin arch from its rock anchor. The common denominator across all 3 disasters remains a persistent blind spot, designing a technically sound barrier while failing to understand the volatile ground designed to support it. Congress passed the Reclamation Safety of Dams Act in 1978, establishing the Federal Safety of Dams program to systematically inspect and modify high-hazard structures. This policy shift permanently altered design standards, elevating internal erosion protection to a primary engineering requirement. Graded sand and gravel filter zones, which were omitted at Teton, became mandatory barriers separating erodible soil cores from fractured rock foundations. Modern protocols also enforce a strict separation between original design teams and independent review boards to prevent institutional blind spots. Yet, the legacy of the old approach remains. Thousands of aging earth-filled dams built under outdated standards continue to operate across the United States. For today's engineers, Teton is not a historic anomaly, but an ongoing warning that safety relies on active monitoring and modern retrofits. Today, thousands of aging dams face the same silent pressure. Teton remains a stark warning. We do not build on the earth, we build with it. When design ignores geology, water always finds the floor. Share your thoughts in the comments below.